We have a rectangular circuit moving to the right as shown in the picture, and as it moves to the right it enters a magnetic field region where magnetic field is uniform and is pointing out of the page, which is perpendicular to the plane of the circuit. Now the question is, what is the direction and magnitude of the induced current in the loop? Let's apply Faraday's law to find the magnitude of the induced current. The magnitude of the induced EMF is equal to the absolute value of the time derivative of the magnetic flux through the circuit. So we can replace the induced EMF with I times R using Ohm's law. That's the left hand side of our equation. And the right hand side of our equation can be replaced with d dt of B times A times cosine 0. Why do we have 0 for the angle? Because the magnetic field is perpendicular to the plane of the circuit, so the magnetic field vector and the area vector are parallel. The angle between them is 0. Cosine 0 is 1. Now the magnetic field is uniform. We can take it out of the derivative, but area is changing. By area we mean the area inside the magnetic field region. Initially the circuit is outside of the magnetic field region and it's being pulled into the magnetic field region. So the area that is in the magnetic field region will change with time, and that's where the change comes from. That's what changes the flux. So then I have I times R equals B times dA dt. Now what is the rate of change of that area? We can model the area as the length, the vertical side of the rectangle. So like so. So this could be capital L. Sorry. Capital L right here. Times the horizontal distance as the circuit is pulled towards the magnetic field region, right? So I'm going to call this horizontal distance x, and this is what changes. The horizontal side of the area is changing, but the vertical side, capital L, is not changing. So I model the area, or I formulate the area as capital L times x, where x is changing as the circuit is being pulled towards the magnetic field region. So then A is L times x, and dA dt is L times dx dt. Because L is constant, again I pull it outside of the derivative and I just have dx dt here. And dx dt is simply equal to the speed at which the circuit is being pulled towards the magnetic field region, which is just v, 3 meters per second in the problem. And then we rearrange our equation to isolate the current, induced current I. Induced current I is equal to B times L times V divided by capital R. Again, B is the magnetic field magnitude, L is the vertical side of the rectangular circuit, V is the speed at which the circuit is being pulled towards the magnetic field region, and R is the resistance in the circuit. The result of the numerical calculation is 0.225 amps. What is the direction of the induced current? As the circuit is being pulled towards the magnetic field region, the flux, initially being 0, increases in the direction out of the page. So initially the circuit has 0 flux in it. As it enters, as it moves towards the magnetic field region, we get a flux through our circuit out of the page, and that flux is increasing because the area is increasing. Now because the flux out of the page is increasing, the circuit is going to oppose that by creating a magnetic field in the opposite direction. Remember, the magnetic effects or induced EMF, induced current, those are all oppositional. So in order to create a magnetic field into the page, what must be the direction of the induced current in the circuit? Align your thumb into the page, that's the direction of the induced magnetic field. Your fingers point in the clockwise direction, your fingers curl in the clockwise direction. So clockwise is the direction of the induced current as the circuit is being pulled into the magnetic field region. Now, what's the magnitude and direction of the induced current once the circuit is completely inside the magnetic field region and it's still moving to the right within the magnetic field region? In that case, the flux will not change because the magnetic field is uniform and the area is now fully inside the magnetic field region. Because there's no change in flux, there will not be any induced EMF. And if there's no induced EMF, there will be no induced current. What is the direction and magnitude of the induced current as the circuit is being pulled out of the magnetic field? Now the circuit is being pulled out of the magnetic field at the same rate, so the area is changing at the same rate. This time the only difference is that the area is decreasing. So the magnitude of the induced current will be the same because V is the same, but the direction of the induced current will be in the opposite direction, in the counterclockwise direction, because this time the magnetic flux pointing out of the page is decreasing. So the loop will oppose to that by creating a magnetic field in the same direction. In order to create a magnetic field out of the page, the current has to be pointing in the counterclockwise direction. So align your right thumb out of the page, your fingers curl in the counterclockwise direction. That's the direction of the induced current as the circuit is being pulled out of the magnetic field region. Here's a quick sketch of the induced current as a function of time. We assume that clockwise is the positive direction for the induced current. As the circuit is being pulled into the magnetic field region, the value of the current is positive 0.225 amps. Once the circuit is fully inside the magnetic field region, the current drops to 0. And once the circuit starts getting out of the magnetic field region, the current value becomes equal to negative 0.225 amps.